It's 2:47 a.m. A pull request lands on a critical payment service repository. 42 files, 50,000 lines of diff. The on-call engineer in Singapore is on her lunch break, and the deployment window closes in 12 minutes. She skims the code. The continuous integration tests all show green. She clicks approve and gets back to her meal. 6 hours later, duplicate charges start hitting the ledger. By the time the bleeding stops, it's a $2.3 million loss, triggered by a partial failure state in the transaction rollback. The initial code compiled and the tests passed, but buried in those 50,000 lines was a single missing finally block. Without it, the rollback logic never fired. No human skimming a massive diff caught it, and standard linters missed it entirely. The immediate reaction from engineering leadership is usually to drop a basic large language model onto the repository and instruct it to review everything. Faster, more urgent tone. The bot immediately starts flagging missing trailing commas and suggesting method extractions. Within 3 days, developers train themselves to scroll past the noise. 2 weeks in, they disable the bot entirely. We call this learned helplessness. Highlighting syntax errors while missing a multi-million-dollar vulnerability reveals a systemic breakdown in scope discipline. Alert fatigue is an architectural failure. In the previous chapter, we built the code generation agent, a system that refuses to trust its own output, relying on a strict test-first verification loop before writing a single line of implementation. This graph details where this case study sits in the 30-agent tree. We built the automated code review agent by taking that exact verified don't trust ethos and pointing it outward. Instead of verifying its own code, it verifies a human's. From the PR landing, we hit the scope filter. It ignores minor style nits, targeting only absolute blockers. This feeds into the verified diff step, checking complex logic, like missing finally blocks, that standard tests miss. The system operates on one ruthless rule. It is programmed to flag only what a senior engineer would actively block a deployment for. Offloading the validation to a structured, disciplined pipeline takes a noisy text generator and turns it into an integrated, zero-friction gatekeeper. A single massive pull request cannot trigger endless model calls. If it does, your API costs will spiral out of control before the week is over. To prevent this, the planning agent acts as the orchestrator. It checks existing CI logs. If a linter already ran, it skips style checks. If a static analysis scan passed, it reduces the security pass. This dynamically allocates a strict budget of 5 model calls per PR. Before running checks, the memory agent grounds the review by loading the organization's specific style guide and global security thresholds, like the OWASP Topcat, directly from a vector store. But the perception layer faces a hard physical limit. A 50,000-line diff cannot fit into a standard context window without truncating vital cross-file dependencies. The agent processes massive diffs using a sliding window file pass. Files are chunked at function boundaries with a 512 token overlap, ensuring critical logic survives the cut. Code that hasn't changed is compressed. The system summarizes these untouched sections down into dense mathematical vectors. These summaries are processed using sentence-BERT embeddings, generating high-dimensional vectors that allow the agent to mathematically compare logic across different files. This maintains the import graph. The system tracks its context even if used incorrectly far away in file B. This perception layer feeds a compressed, fully contextualized map to the reasoning core, solving the primary bottleneck of reading massive codebases. Now the system can reason. The chain of agents orchestrator runs 4 sequential passes: style, security, test coverage, and logical correctness. Each pass uses a strict prompt structure: persona, task, context, format. This physically restricts the output to specific severity tiers: blocker, critical, warning, or info. This table maps out what can go wrong when deploying automated reviewers, contrasting failure modes with architectural guardrails. Look at the top row. But what if the agent hallucinates a vulnerability? The verification agent steps in as a safety mechanism, intercepting every single flagged blocker. Flagging a missing finally block triggers the agent to parse the code into an abstract syntax tree, simulating control flow to test the vulnerability. This gate is probabilistic. Below 90% confidence, the blocker is downgraded and omitted. The final output is stripped down to a simple markdown table and a single deterministic line of text. The continuous integration system greps that line to automatically block or approve the merge. A probabilistic simulated verification loop is exactly how an automated system confidently catches a missing rollback path without flooding the pull request with noise. This architecture isn't theoretical. By 2026, multi-pass review agents are actively deployed across the software engineering industry. At the top, the incumbent platform provides broad ambient pair programming directly in the developer workflow. Pure-play review specialists and open-source challengers are capturing market share precisely by prioritizing high-signal, zero-noise verification passes. Enterprise deployment requires strict IP provenance and data security. Self-hosted, data-isolated models hold a structural advantage when dealing with strictly regulated codebases. This dashboard outlines the tangible business impact of properly deploying this specific agentic architecture in the field. Pay close attention to the 1-week metric. Let's return to that 2:47 a.m. scenario in Singapore, but this time replay it with the full agentic pipeline installed on the payment repository. The pull request lands. The sliding window algorithm safely ingests all 42 files and 50,000 lines within minutes, preserving the exact import graph. The reasoning loop spots the vulnerable rollback path. The verification agent simulates the partial failure state, confirms the missing finally block, and clears the 90%